Hello everyone. Today, we're going to talk about zinc oxide and its role in the construction industry, focusing on its potential health and environmental impacts. This presentation is part of a larger project funded by the European Union creating course material exploring the use of nanoparticles in the construction industry and how life cycle analysis can support making better decisions. Today, we're looking specifically at zinc oxide, but check out the other course material to explore further nanoparticles. This project is a collaboration between the University of Sevilla, National Technical University of Athens, Chalmers University of Technology, the Centro Tecnológico del Mármol, and Delta MPIS with the support of the European Union. We'll begin by covering what zinc oxide at the nanoscale is, exploring how it's made, and then examining its primary uses. We'll also consider some of its health and environmental impacts before looking into how life cycle assessments, LCAs, can deepen our understanding of these effects. Lastly, we'll review some recent studies on zinc oxide nanoparticles and their environmental footprint. Let's get into what makes zinc oxide nanoparticles unique. They are versatile, with a broad range of applications thanks to their specific properties. Antimicrobial properties make them valuable in healthcare products. Pharmaceutical uses include drug delivery systems and wound care. Semiconductor abilities contribute to their use in electronics and solar cells. UV absorption makes them a staple in sunscreens and protective coatings. Zinc oxide nanoparticles are highly adaptable in shape and size, offering even more flexibility. They can be engineered as spheres, ribbons, rings, or even wire-like structures. This adaptability allows each shape to serve different purposes, enhancing the nanoparticle's functionality across applications. In addition to its diverse applications, zinc oxide exhibits several key properties that make it a valuable material. Optical transparency, it allows light to pass through, making it useful in transparent coatings and displays. Semiconducting behavior, this property enables its use in electronic devices and sensors. Piezoelectric effect, it generates electricity when subjected to mechanical stress, making it useful in energy harvesting devices. Thermodynamic stability, it remains stable under various temperature and pressure conditions. Low toxicity, it's generally considered safe for most applications. Furthermore, zinc oxide nanoparticles specifically offer antimicrobial properties, making them effective against bacteria and fungi. Other key properties of zinc oxide include density, approximately 5.61 grams per cubic centimeter. Melting point, it sublimates directly from a solid to a gas state at around 1,300 degrees Celsius. Band gap, approximately 3.37 electron volts. Binding energy, around 60 millielectron volts. Approximately 8,000 tons of zinc oxide nanoparticles are produced annually. There are two primary methods to synthesize these nanoparticles, chemical and biological. Chemical methods are the most common and include sol gel, a solution-based technique involving the formation of a sol and its subsequent gelation. Solvothermal, a high-temperature and high-pressure method using solvents to synthesize nanoparticles. Continuous hydrothermal, a continuous flow process that allows for large-scale production. However, there's growing interest in biological synthesis methods as they offer potential environmental and energy benefits. These methods involve microorganism-mediated synthesis, using bacteria or fungi to produce nanoparticles. Plant source-mediated synthesis, utilizing plant extracts to synthesize nanoparticles. Let's take a closer look at the sol gel process, a popular chemical synthesis method. It starts with dissolving a precursor, often zinc acetate, in a solvent. A stabilizer is added to prevent clumping, and through a series of steps, including gelation and heating, we obtain the final zinc oxide nanoparticles. The sol gel method offers good control over the size and shape of the nanoparticles, making it a versatile technique for various applications. Another common chemical synthesis method is the solvothermal method. The solvothermal method involves a high-temperature and high-pressure process. Here's a breakdown of the steps. Precursor preparation: a metal salt, such as zinc nitrate or zinc acetate, is dissolved in a suitable solvent. Hydroxide formation: a compound containing an OH group, like a base or alcohol, is added to the solution. This leads to the formation of a zinc hydroxide complex. Solvothermal reaction: the reaction mixture is heated in a sealed vessel under specific temperature and pressure conditions. These conditions promote the formation of zinc oxide nanoparticles. Product recovery: once the reaction is complete, the nanoparticles are recovered by filtration or centrifugation, followed by washing and drying. The solvothermal method allows for precise control over the size, shape, and crystallinity of the nanoparticles, making it a valuable technique for various applications. An exciting, eco-friendly approach is biological synthesis using plants. This method utilizes plant metabolites, naturally produced by certain plants, to transform metal salts into zinc oxide nanoparticles. It's sustainable and potentially scalable, though less precise in controlling nanoparticle size and shape compared to chemical methods. Plant source-mediated synthesis utilizes secondary metabolites naturally produced by plants. These metabolites act as reducing agents, converting metal salts, precursors, into the desired metal oxide nanoparticles, in this case, zinc oxide. Here's how it works. Plant selection: specific plants are chosen based on their known production of relevant secondary metabolites. Extraction: different solvents with varying polarities are used to extract these metabolites from the plant material. Nanoparticle formation: the extracted compounds are then used in a reaction with metal precursors, often at room temperature, to form zinc oxide nanoparticles. This method offers several advantages. Environmentally friendly: it avoids harsh chemicals and high-temperature conditions often used in traditional methods. Sustainable: it utilizes renewable resources and potentially reduces waste. Scalability: depending on the chosen plant source, this method has the potential for large-scale production. However, plant-based synthesis can be less precise than chemical methods in terms of controlling the size and shape of the nanoparticles. Zinc oxide has a vast range of applications. Here are some major sectors where it's used: cosmetics and pharmaceuticals, for sunscreens and antibacterial products, construction materials, as additives in paints and coatings to boost durability, optoelectronics, in displays and LEDs, environmental remediation, to degrade pollutants, gas sensing, detecting harmful gases, abrasives and polishing agents, in cleaning and polishing applications. Let's delve deeper into two of the main applications of zinc oxide: cosmetics and pharmaceuticals, and construction materials. In cosmetics and pharmaceuticals, examples include UV protection. Zinc oxide's strong UV absorption properties make it a key ingredient in sunscreens, protecting skin from harmful UV rays. Antimicrobial properties. Its antimicrobial nature makes it useful in various medications like antifungal and antibacterial creams and ointments. Wound healing. Zinc oxide can accelerate wound healing and reduce inflammation. Emerging applications. Exciting research suggests potential future uses in drug delivery systems and cancer treatments. In construction materials, examples include rubber. Zinc oxide improves the mechanical properties of rubber, making it more durable and flexible. Concrete. It enhances the workability and water resistance of concrete. Coatings. Its UV-absorbing properties make it suitable for use in protective coatings for buildings and other structures. Now, let's explore some of the more specialized applications of zinc oxide. In optoelectronics, solar cells, zinc oxide's optical and electrical properties make it a promising material for use in desensitized solar cells. UV light-emitting devices. Its ability to emit light in the UV spectrum has applications in various devices. In environmental remediation, water purification, zinc oxide's photocatalytic properties allow it to degrade pollutants in water, such as dyes and organic contaminants. In gas sensing, gas detection, zinc oxide nanostructures, particularly those with high surface-to-volume ratios, are excellent gas sensors. When gas molecules interact with the surface of these nanostructures, changes in electrical resistance occur, enabling the detection of various gases like carbon monoxide and nitrogen dioxide. While zinc oxide is generally safe, it's important to be aware of potential health effects, particularly when dealing with nanoparticles. Potential health effects: zinc fever, a short-term flu-like illness caused by excessive zinc oxide inhalation. General toxicity: the toxicity of zinc oxide nanoparticles can vary depending on factors like size, shape, and surface chemistry. Oxidative DNA damage: exposure to zinc oxide nanoparticles can lead to oxidative stress, which can damage DNA. Systemic inflammation: in some cases, zinc oxide nanoparticles can trigger inflammation throughout the body. Prevention measures: to minimize health risks associated with zinc oxide nanoparticles, it's crucial to proper handling, use appropriate personal protective equipment, such as gloves, masks, and protective clothing. Ventilation: ensure adequate ventilation in work environments to reduce exposure to airborne particles. Safe disposal: follow proper waste disposal guidelines to prevent environmental contamination. Risk assessment: conduct thorough risk assessments to identify and mitigate potential hazards. Let's delve deeper into the specific health effects associated with zinc oxide nanoparticles. 4.1. Oxidative DNA damage. Occupational exposure to zinc oxide nanoparticles has been linked to oxidative DNA damage, which can increase the risk of cancer. 4.2. Zinc fever. Inhalation of zinc oxide nanoparticles can lead to a condition known as zinc fever. Symptoms include throat irritation, coughing, metallic taste, and other flu-like symptoms. Long-term exposure to zinc oxide nanoparticles has been associated with an increased risk of cardiovascular disease. 4.3. Systemic inflammation. Exposure to zinc oxide nanoparticles can trigger inflammation both locally in the respiratory tract and systemically, leading to various health issues. 4.4. General toxicity. The toxicity of zinc oxide nanoparticles depends on several factors, including their chemical composition, size, shape, surface properties, and exposure duration. High exposure levels can lead to adverse health effects. To mitigate the potential health risks associated with zinc oxide nanoparticles, it's crucial to implement effective prevention measures, personal protective equipment, PPE respirators. Using appropriate respirators can significantly reduce inhalation exposure. Protective clothing. Wearing gloves, lab coats, and other protective clothing can minimize skin contact. Medical surveillance. Regular health monitoring can help identify early signs of exposure-related health issues. Regulatory compliance. Adhering to occupational exposure limits and record-keeping requirements can help ensure worker safety. By implementing these preventive measures, we can minimize the risks associated with zinc oxide nanoparticles and promote a safer working environment. Turning to environmental impacts. Zinc oxide's antimicrobial properties, while beneficial, can harm beneficial microbes in wastewater. Excessive exposure can also be toxic to plants, algae, and marine life, particularly for organisms prone to bioaccumulation. While zinc oxide is generally safe for humans, it can have significant environmental impacts. 5.1. Toxicity. Microorganisms. Zinc oxide's antimicrobial properties can be detrimental to beneficial microorganisms in wastewater treatment systems. Plants. While moderate doses can promote growth, excessive exposure can be toxic to plants. 5.2. Toxicity to aquatic organisms, algae and invertebrates. Zinc oxide can damage the cells of aquatic organisms, including algae and invertebrates. Marine invertebrates. Marine organisms are particularly vulnerable due to their susceptibility to bioaccumulation and pollution. Effects can include oxidative stress, morphological abnormalities, and developmental issues. To fully assess the environmental impact of zinc oxide, we can conduct a life cycle assessment, LCA. An LCA analyzes the environmental impacts of a product or process throughout its entire life cycle, from raw material extraction to end-of-life disposal. For example, a study by Steberova et al., 2017, assessed the environmental impact of zinc oxide nanoparticles synthesized through a continuous hydrothermal process and used in a self-cleaning coating. By conducting comprehensive LCAs, we can identify potential environmental hotspots and explore ways to minimize the negative impacts of zinc oxide and other nanomaterials. To conduct the LCA, the study followed the guidelines of the ISO 14044 standard. Our goal was to compare the environmental impact of zinc oxide nanoparticle production to traditional zinc oxide production. Scope: we focused on the cradle-to-gate stage, from raw material extraction to the production of zinc oxide nanoparticles. Functional unit: we defined the functional unit as 1 kg of zinc oxide nanoparticles. Database: we used the EcoInvent3 database to obtain environmental data. Characterization method: the recipe method was used to assess the potential environmental impacts. Key assumption: a key assumption in this study was that there were no significant releases of zinc oxide nanoparticles into the environment during production. This is because specific characterization factors for zinc oxide nanoparticles were not available at the time of the study. Let's discuss the results of the LCA, ZNO production, chemical usage. The production of zinc oxide nanoparticles, particularly through chemical methods, relies heavily on chemical inputs. This contributes significantly to the overall environmental impact. Promoting biological synthesis. To reduce the environmental footprint, there's a strong case for investing in and developing biological synthesis methods, which use natural processes to produce nanoparticles. Product comparison: reduced environmental impact. When comparing products containing zinc oxide nanoparticles to traditional products, the nanoparticle-based products often demonstrate lower overall environmental impacts. Savings in use phase: these savings primarily stem from the improved performance and durability of products containing zinc oxide nanoparticles. For example, a self-cleaning coating with zinc oxide nanoparticles may require less frequent cleaning and maintenance, leading to reduced energy and water consumption. The literature referred to in this flashcard can be found here. Literature continued. In conclusion, zinc oxide nanoparticles offer a wide range of applications with the potential to improve our lives. However, it's essential to balance these benefits with a thorough understanding of their potential health and environmental impacts. By conducting comprehensive life cycle assessments and implementing appropriate safety measures, we can harness the power of these nanoparticles while minimizing their negative consequences. We hope this example of a nanoparticle in the construction sector has been helpful and puts the material you have studied in the NanOER course into context. Enjoy the rest of the course.